PhD. He then was very wise and escaped the country over to America to do his first postdoc was at Columbia with Joyce Hirsch, yeah. And then you went on to Northwestern with Marcel Megelam, am I right? Yeah. And then you moved to Duke University, I think, was that 15 years ago now, something like that, where you set up the Egner lab, where you've just gone from strength to strength. I'm not going to go into the ridiculous H indexes and IH indexes and the amount of money that you've brought in, because it's just, yeah, I think it's much better to listen to you and hear about what you've got to say today. So please, Tobias, take it away.
Wow. Thank you very much for the kind introduction and for the award in the first place. A great honor, very unexpected, which is the best kind of good thing. It's a large positive reward prediction error that I experienced. When was it in November? I didn't know I was nominated for anything. It's like an award, me? That's exciting. So thank you very much for that. I've been treated as an honorary Brit for my history on this island, as you've heard. Great. I'll jump right in. I'll do a little talk today on some of the work we've been doing over the years. Hopefully it will be sort of coherent and hopefully it will end on time, more or less. So if you're anything like me, you'll enjoy occasionally doing work in a coffee shop. And as you read a paper or write a paper, you might notice how your attentional focus tends to sort of wax and wane in unison with the amount of chatter around you from the other patrons in the coffee shop. So you'll tend to focus more on the paper when the noise around you, when the level of distraction goes up, and you can ease off your attentional focus from the paper if it is a quiet environment. But even when you're really strongly focused on that paper, while things are a bit noisy, you're still perfectly capable to switch away from this task of paper reading to a different task. For example, your phone rings. So this is a nice example, or this sort of very mundane event illustrates two major capacities of our cognitive system. One is called cognitive stability, so the ability to focus on a given task while pretty much filtering out distracting information around you, irrelevant stimuli, and cognitive flexibility, which is the ability to then nevertheless switch away to doing a different task if either your internal goals or the external circumstances change, and it would be beneficial to do so. So cognitive stability and flexibility can be thought of as sort of like core characteristics of cognitive control, and more specifically, we can think of them as characteristics of working memory. So I have here a little, very simple cartoon that's trying to capture a very popular or influential neurocomputational model of working memory by Frank and O'Reilly. The idea is then that a task set, so the current rules of the game, focus on the paper reading, ignore auditory chatter around you, is being held in working memory. We can think of that as a procedural working memory as opposed to declarative working memory of items. And by dint of being in working memory, it is shielded from other information, and it is being used to bias how we process incoming stimuli and how we select actions, right, in line with the current rules of the game. However, as noted earlier, we're of course capable of switching out this particular task set and allowing different tasks set into working memory if we need to perform a different task. And here the idea is that there is a flexible gating mechanism that allows access to working memory if need be. So we can then replace task set A with task set B if that input gate is open. And you'll all be familiar with the idea perhaps that maintaining a task set in working memory is typically associated with activity in frontoparietal cortex that might serve to shield this task set and bias information processing. Whereas this input gating mechanism of working memory to allow new information into working memory has been associated with the basic ganglia, specifically the dorsal striatum in the thalamus. So now importantly, the strength with which you protect this task set in working memory and the ease of switching it out don't stay static over time, as you've seen in this example earlier in the coffee shop, but other, they're dynamically adjusted. So you tend to adjust the strength of focus with the changes in the environment to match the demands. And the same is true for the ease of switching. So we can think of these as being dynamically regulated. And it's really these mechanisms by which task focus and task switching are being regulated that I'm most interested in. Some people think of that as method control, because you're controlling or regulating how you use these control mechanisms. Again, the task set can be enhanced or eased off depending on demands. And similarly, right, if you were expecting a phone call, for example, you'd be quicker to switch to the phone than if you're not expecting a phone call. So the ease of switching also can be adjusted to suit your circumstances. Now, importantly, the regulation of task focus and task switching, or stability and flexibility, is heavily impaired in many clinical conditions, for instance, in autism spectrum disorder, ADD, and many others. So these kids have great difficulty matching their use of their, the machinery that allows them to focus on a certain task to match that with the appropriate context. And the same is true for switching and flexibility. So how do we think about this these processes? How do we regulate task focus and switch readiness? And this is the topic of the talk today. So I have a little thesis here. And since you've been to a few talks before, you might have the suspicion that I will later resell you this thesis as my conclusion, and you would be correct in this assumption. So you already know what the story will be. Task focus and switch readiness are adapted according to the same types of learning principles. It's something I'll try to convince you of today, but they can be regulated independent of each other. And I'll walk through this in 3 little chapters here. First, describing how people adapt task focus to changing demands, then how people adapt switch readiness to changing demands. So this is stability, flexibility, and then how these two processes seem to play out independently of each other. All right, let's jump into the first. So how do we model this regulation of task focus in the lab? Now, you're all familiar with one model thereof, and this is the classic color word Stroop task, for example. So in the lab, we can have tasks that challenge task focus by having a task that has potent distractors baked into it. So in this classic color naming Stroop task, the participant needs to name the in-colors of these color words, and the color word meaning can be congruent or incongruent with the colors. And as you all will have probably experienced, when they're incongruent, because we are very, word reading is a very prepotent process. We're very practiced at word reading. These word meanings will interfere with the process of naming the in-colors. And this is essentially a competing task to the one that you've been instructed to. So it's a nice model of task focus, because we can measure sort of how much an uninstructed task interferes with the one that you're actually supposed to be doing. Now, the reason that this is an interesting model also for understanding the regulation of task focus is that the Stroop task and similar tasks show very interesting patterns of sequential behavior. And here's a sort of a famous paper from quite a long time ago now, where Gabriel Dacron and colleagues showed that this type of task is subject to trial history effects. And one type of trial history effect is the so-called congruency sequence effect. This is just defining that if the previous trial that you've just experienced was a compatible or congruent trial, so an easy trial, where you didn't suffer interference, the next trial will have, on average, a larger congruency or interference effect than if the previous trial was an incompatible trial. The heuristic here is quite simple. The idea is, if you just encountered a challenge to your attentional focus, an incongruent trial, presumably that does something in the brain that upregulates attentional focus for the next trial, where then, if you encounter another incongruent trial, you're better at ignoring the word meaning. You're thus better at resolving this interference. And you can find the same type of adaptation at a longer time scale at the block level of trials. So here, and people have done this a lot, you can manipulate the proportion of incongruent relative to congruent trials across blocks of trials. And a very, very replicable finding is that the average interference effect, so again, the difference here in performance between incongruent and congruent trials, will be much larger in a block where incongruent trials are relatively rare than in blocks where they are relatively common. And the same logic applies. The idea is that, oh, maybe what people are doing, they adjust their level of focus to match these changing demands. And if you're encountering a lot of difficult trials in the block, you somehow upregulate how much you pay attention to the relevant task feature, and therefore you're better at keeping the interfering information out. How does this play out more mechanistically? Well, there's been a very influential model formulator put forward by Botvinnik and colleagues over 20 years ago now, the so-called conflict monitoring model. The way this works is a connectionist model where they have a task demand unit. You can think of this as the working memory in my sketch earlier that holds the rules of the game in mind, and it tries to bias the processing of the display color and the word meaning. In this case, it will try to enhance the processing of color, suppress the processing of word information. Both of these pieces of information, however, impinge on the response layer of this model. And when you encounter an incongruent stimulus, of course, they will elicit two incompatible responses. And this is what these authors call conflict. And conflict will cause a delay in responding and cause sort of on average less accurate responding. But the key of this model is that in order to account for these adaptation effects, they posit that, well, we have in our brain a device for monitoring how well we're doing. They call this a conflict monitor, basically measuring the level of co-activation in these units. And when the level of co-activation is high, this is a sign for you not doing so well, right? It means like you don't know what response to give. That's not a good thing. So the conflict monitor detects this, passes this information back to the task demand units and working memory, and basically says, hey, we're not doing well. You have to enhance the top-down biasing in order to shield our processing better from the distractors. So the idea is then, after a trial like this, conflict is high, we'll reinforce task demand units. Thus, on the next trial, conflict will be relatively low if you encounter another incongruent trial. Does that make sense? Another way, when we want to dig a little bit further into the underlying computational machinery of this, and this is in fact how this was modeled in this case, it's essentially a reinforcement learning model. Like they use a temporal difference learning algorithm. You can think of the current level of top-down biasing as the anticipation of upcoming control demand. How difficult is the next trial going to be? That is then encounters the actual observation of demand. Depending on what your predictions were, you'll have some level of prediction error. In this case, it's not a reward prediction error, but a control demand prediction error. For example, you might have thought it's going to be easy, but it was actually hard. So you have a prediction error in that particular direction. And you can then use this prediction error to update your prediction for the forthcoming trial. It's an ongoing incremental learning process. Importantly, the prediction error in that update gets multiplied by the so-called learning rate. We heard about this yesterday a little bit. The learning rate is essentially determined, so you can think of the prediction as a running average of the trial history of the control demand in this case. And the learning rate really determines how many trials you take into account in that running average. And if the learning rate is high, it means you only take into account very recent pieces of information. If the learning rate is low, it means you take into account a lot of trial history, a longer trial history. Now, this model can do very well at simulating these effects you saw on the previous slide, so this trial-by-trial effect and the blockwise effect. But it has a major problem, and that is it needs to use radically different learning rates to simulate both of these effects. So for the trial-by-trial effect, it needs to have a really high learning rate. For the block level effect, it needs to use a really low learning rate. The problem with this is that both of these effects occur simultaneously in the same data. So the model cannot possibly explain both of these at the same time. This is a problem that we noticed many moons ago. My former PhD student, Jifang Zhang, is a professor at the University of Iowa now, therefore set out to think about how do we overcome this issue of this fixed learning rate that they use in this model and that can't really fit both of these phenomena at the same time. And the solution to that is to say, well, we need a flexible learning rate, which is a lot more realistic as well, meaning that we don't, if we interact with a task like that, we don't have a single learning rate that we use throughout how we're doing this task, but rather we change how much we update our expectations based on trial history over time, depending on the trial sequence that we experience. So how do we inform a flexible learning rate? For this, we borrowed some approach from the reward learning literature. A few years before this, Tim Behrens in Oxford, he published a famous paper on volatility, the volatility of the environment being an optimal parameter for tweaking your learning rate in adjusting expectations. And the idea is the following. If you're in a stable environment that has its low volatility, there's not a lot of things changing, you want to have a very low learning rate. You want to take a long trial history into account, because any given surprise could just be a noise event in this kind of environment. You don't want to update your expectations radically to encountering a prediction error. So you weigh down prediction errors by having a low learning rate in a stable environment. By contrast, when you have a volatile environment, things are changing all the time. You want to have a high learning rate, because any surprise that you encounter might be a real signal that, hey, things have changed and you need to change your predictions. Does that principle make sense? Wonderful. So this is what we did. Jifeng essentially built a more nimble version of this model that we call the flexible control model, that incorporated the self-adjusting learning rate that's driven by the volatility, in this case of control demand, meaning how quickly do the demands change in a task? Is it very easy for a while? Is it very difficult for a while? Do I have a lot of variation in this? And using this model, we obviously then we gathered an empirical data set and then fit the model to it. This is a different type of conflict or Stroop type task, a face word Stroop task. Basically, the participant indicates the sort of normative gender of the face stimulus and tries to ignore the word labels written across, produces very reliable congruency effects. And of course, it's a popular task to use in fMRI because people are interested in looking at FFA activity, that kind of thing. Not relevant right now, but what's relevant is that he manipulated the proportion of congruent trials over like 7 levels or so, and you can see the classic effect here that the mean congruency effect goes down as the proportion of incongruent trials goes up. If you analyze the exact same data set collapsed across blocks but trial by trial, you also find this classic trial by trial conflict adaptation effect, right? So both of these things co-occur. The original model can't fit them at the same time. But here we show that this model that incorporates this flexible learning rate can fit them together. So it can, because it self-adjusts the learning rate, it can both account for the trial by trial as well as the blockwise effect. Okay. Question is then, okay, if we really now have a nice model of learning to adapt the focus of attention to changing demands, how does that play out in the brain? Now, as many of you will know, about 20 years ago, there was a real heyday of big impact papers when people first tried to ask or answer this question. And it was very early days of fMRI as well. And the basic approach to answering this question was to compare averages of different trials, of different trial types. So, for example, people just compare the average activity in fMRI elicited by incompatible trials, depending on whether they were preceded by a compatible or incompatible one. And similarly, you would look at blockwise effect of an activity elicited by incongruent trials, depending on whether they were rare or frequent. And the take home always was that, oh, when conflict is high and control is low, we see activity in the dorsal anterior cingulate cortex. When the reverse is true, control is high and conflict is low, we see activity in the lateral prefrontal cortex, as you see here. But these approaches, of course, don't really, they kind of ignore the whole idea of a dynamic learning process, right? Because you just average over like these trials across conditions together, you lose the interesting information that you might glean from really trying to track what's going on from trial to trial. How do people update their expectations of conflict from trial to trial? So this is what we set out to do in this imaging study, again by Jifeng. So here we created another conflict task. We used this face word Stroop task again, and we manipulated the proportion of congruent to incongruent trials over time. And here we did this in conjunction with a volatility manipulation as well. So you see here an example run where in some, we had these blocks of trials, and in some blocks of trials, the proportion of congruency changed frequently. So every 20 trials, and think of this is like low proportion congruent, high proportion congruent, low proportion congruent, high proportion. This is about 20 trials. And in other blocks, it stayed at one level for your aim track. So these are volatile blocks versus stable blocks. Whether the environment is stably easy or stably difficult, lots of incongruent tracks or lots of congruent tracks, or the two alternate quite rapidly. Does that make sense? So for simulating the idea of a more or less a volatile environment. And here you see that if you fit the model to the data, this is just an example from a particular trial sequence subject. The predicted conflict level of the model, right, tracks fairly well the actual distribution. And of course, these little peaks that you see here is like when you encounter a rare trial in a block, right? You think it's going to be an incongruent trial, you encounter a congruent trial, you have prediction error and the prediction changes and so forth. Here, this just shows that, as it should be, the learning rate in the model is in fact adapting to the different conditions. So in stable runs, the learning rate average is very low because it should be, that's optimal. In volatile runs, it's quite high and it changes accordingly. So then to interrogate the neural data, what we did is that we used a multi-voxel pattern analysis approach. Basically, we tried to figure out with a search rate approach where in the brain are there clusters of voxels whose activity patterns allow us to explain significant variance in the model parameters from trial to trial. And this, I'm going to sort of gloss over a lot of detail. It's just going to run through the take-home message here. We found that the control prediction error encoded in the inferior frontal gyrus and anterior insular cortex, that the volatility-driven learning rate was encoded in the anterior insular, so very ventral here, in fact. Very interesting to our mind, because we did not really go into this anticipating a lot of subcortical activity playing a major role here, was that conflict prediction in this model, the updating of conflict predictions was actually carried by the caudate nucleus, but then translated into top-down biasing by the lateral prefrontal cortex. So this was sort of the expected result, whereas these were a little less expected. But this it sort of goes to show for us the take-home message was that when you take the learning process seriously in a cognitive control experiment, you sort of add a subcortical learning machinery to the classic regions of the ACC and lateral frontal cortex that you find when you compare average condition estimates with each other. So we basically concluded that especially the anterior insular and caudate nucleus are involved in tracking the demands in the environment and then informing frontal cortex, which then implements adjustments accordingly. For fans of the anterior cingulate, worry not. Then you can do other analysis where the ACC will show up, but it plays a more reactive control mode, role in control in this particular data set, rather than these more proactive incremental learning mechanisms. This is, of course, correlational data. So in one follow-up study, we set out to test whether this lateral prefrontal focus we revealed in this study was whether we could, probe this with a causal disruption method. Is this area really necessary for mediating these controlled adaptation effects? So we did a TMS study. This was done by Paul Lulekabe, former postdoc in the lab, who's now faculty at Birmingham, actually. I think he just started last year or 2 years ago as an assistant professor there. So when Paul was in the lab, together with Jifang, we took basically the exact locus of this lateral PFC activation from the previous study and said, hey, let's target this with TMS. We do online disruptive TMS. So the idea is we have the same kind of task. And just before stimulus onsets on a subset of the trial, we deliver a little burst at beta frequency, a little burst of TMS over that location. The idea is we essentially inject noise in that region just prior to the subject dealing with the stimulus. We don't want to do during the stimulus because we don't want to mess with perceptual and motor processes. And the whole idea of our model is that it's a proactive model, right? People are anticipating and they're implementing control in advance of the stimulus. So if that is true, this should mess up sufficiently the processes in PFC to disrupt the adaptation process. As a control site, we use S2, so somatosensory cortex, where you think, this shouldn't really do anything. to the process here, but is a decent control for just the actual delivery of TMS and the discomfort associated with this and so forth. So we did this, and here you see that we manipulated over blocks of trials a proportion of congruent trials again. This again allowed us to both look at this longer-term adaptation effect over blocks of trials as well as the trial-by-trial adaptation effect. And here's what happened. So you see first for the more phasic effect, the congruency sequence effect, so the trial-by-trial effect, the control session, we replicate the classic finding. Congruency effects are reduced after incongruent trials compared to congruent ones, so the classic conflict adaptation effect. However, in the LPFC session, this effect is basically abolished, so not happening anymore, the adaptation. Same happens when we look at the listwise proportion congruent effect. So here again, the control session just replicates the classic finding. You get a smaller average congruency effect in the conditions where there's a lot of incongruent trials. But when you mess with this particular lateral PFC location prior to trial onset, you remove this effect as well. That's providing some, tentatively causal proof of this region being important in implementing these learned predictions of how much we need to adjust our focus on a task. All right, I do a little interim summary. People adapt their task focus to changing demands over time. I hope that is fairly clear, fairly obvious. This proactive process seems to be explained or can be explained by an incremental learning process of RL-type learning process, ideally with a volatility-driven learning rate that does better than fixed learning rates. And the adaptation of cognitive stability, which is how we think of this task focus manipulation, seems to involve the interplay of AI subcortical regions, particularly the caudate, as well as ACC and lateral PFC. All right, that gets us to the second part of the talk. Now I want to just pivot from the cognitive stability part, so focusing on a task and altering how much you try to suppress distractors, to the flexibility piece. How do we switch between tasks? And in particular, I want to talk about how adaptation to changes in how much we have to switch, how they play out in a very similar manner to those adjustments that we've seen in the changes in task focus demands. As you all know, in daily life, we do switch between different activities a lot. As we know from a very long cognitive psychology literature, switching between tasks incurs a cost. So, right, if you switch task versus repeated task, you have slower reaction times, you tend to have lower accuracy, and this task switch cost is an extremely reliable finding. Now, interestingly, however, task switch costs are subject to the exact same type of adaptation effects as the conflict effects are. And there's many examples of this in the literature. I just walk you through one of them that happens to be from one of our recent studies. We've done a bunch of these studies, and so have other people. What you see there is a very classic task switching paradigm. I think it's pioneered probably by Steve Monsell years ago. And in this paradigm, you see a single digit on each trial, and you perform one of two tasks on this digit, depending in this case on the color of the digit. It cues you to the task here. One of the tasks is to decide whether the digit is smaller or larger than 5. So this is usually 1 through 9, excluding 5. So you just say, hey, this is smaller than 5, this is larger than 5. The other task is to decide whether it is an odd or an even digit. So odd or even, you get the idea. This might be, a parity task for the red cue. You say, yeah, that's an even stimulus. Then it happens to be a task switch. Now you have to say that 6 is larger than 5 rather than being an even stimulus, and so forth. So when you run this, you have either task repeat and task switch trials. You get a large, robust switch cost. And what we did here and what others have done in the past is to manipulate over blocks of trials how many switch trials you encounter. So in one block, it was 25% switch trials, another one 50%, another one 75% switch trials. And you see here in both accuracy and response time, very lawful scaling of the switch cost with the frequency of switching, right? So again, it seems that we're adapting to the demands by somehow getting more ready to switch, incurring much smaller costs when we have to switch a lot in a particular environment than when we have to switch rarely. And in this particular experiment, I picked this one out because it has an FMI component to it. So we also pursued sort of a model-based FMI analysis strategy here too. And we first fit a reinforcement learning model to individual trial sequences and subjects in this protocol. So here the idea is that people learn to predict the likelihood of a task switch. And you can do that. You can fit the data nicely. I just show a single aspect of this here, where the model, if you look at the prediction error quartile, a prediction error obviously should scale with reaction time, right? Because the less expected the trial is that you encounter, the longer it should take you to respond to it. So this is just a little sanity check from the model. But then ultimately what we use the model for is to analyze the fMRI data. So primarily in this case, we're interested in fitting the prediction error, the variation, trial-by-trial variation in prediction error, switch prediction error in this case, to the fMRI data and finding where in the brain do we find correlates of this, tracking the updating of switch predictions. This is somewhat busy, but we have here plotted on the same slices the basic switch effects, so switch over repeat, and you see a very classic frontoparietal network activated there. And then importantly, the modulation of activity by switch prediction over trials. And you see that that activates mostly, well, partly unoverlapping, but partly overlapping regions, very much focused on interparietal sulcus type area, as well as some lateral prefrontal cortex area as well. And the overlap is kind of interesting because it suggests that the same regions are involved in, the actual switch process are also involved in updating expectations about whether switching is likely in the future, right? Nudging the expectations for this up and down from trial to trial. What we didn't find in this particular study, though, is any basal ganglia involvement, which we were thinking would be more likely. The idea that this input gating to working memory would be perhaps modulated by the switch expectations, but that might be generally a little bit harder to find for a variety of reasons. We've seen basal ganglia activity very strongly associated with gate opening and closing processes in a different type of working memory study, but not in this study where we were interested in switch adaptations. So just a quick summary of this. The take home from my point of view is that we have a very similar kind of signature of behavior here. So like cognitive stability, cognitive flexibility seems to be dynamically adjusted to suit different demands over time. And frontoparietal cortex seems to track this incrementally learned predictions of how likely it is that I have to switch over time. Now, you might wonder, well, frontoparietal cortex, that's the same kind of areas that are always activated in these Stroop type tasks. So you might wonder, how do these things relate to each other, right? How does task switching or regulating task switching relate to regulating task focus? Very well justified question, because if you took like a couple of meta-analysis, for example, an fMRI, one that's dedicated to conflict processing, another one to task switching, and you looked at the activations, you would find very, very much overlapping regions. So one possibility is like, well, maybe it's the same region doing both of these things. We have not approached this particular subject in an fMRI study yet, although we're currently finishing some data collection on it, but it really speaks to the more the broader sort of cognitive question of whether stability and flexibility are intrinsically linked. They're just opposites of each other, like endpoints on a stability flexibility continuum, and maybe these frontoparietal regions are just involved in shifting around the level of stability versus flexibility, or maybe they are independent constructs. And this is going to be the topic of the very last little section of my talk here. So as you can tell, I'll come out on one side of this debate, but it was a surprise because we didn't go in with this expectation. So it's always especially fun if you go into a project and you come in with one set of expectations and you actually have to completely overturn them. So here, just to make this a little bit more tangible, right? The idea or one very common idea in the cognitive science literature is the idea of a stability, flexibility continuum and a trade-off. And you can quite easily see how this might be the case. So for example, you could think that, well, protecting a task set in working memory and this input gate, that should be quite closely linked to you, right? So for example, if you close the gate, that presumably protects the task set in working memory. If you open the gate, that presumably weakens that protection. So it makes it quite intuitive to think that a single mechanism might be associated with both the relative ease of switching and the relative strength of task set protection. And Thomas Goschke has formulated this many years ago quite nicely. He hypothesized the existence of an updating threshold. So you can think of this as related to this input gating mechanism. The idea is that if the updating threshold is low, that means things can easily be updated. That means it's easy to switch, but you can also have a lot of intrusion by distracting information. So you'd be good at switching, but you'd be horrible at protecting your task set against interference. By contrast, if the if the set point on this updating threshold is very high, that means it's difficult to update. So you're not very flexible, but you're very good at protecting your prime task set. Makes sense, right? You have like a very, I think, very intuitive account here of how a stability-flexibility trade-off might play out in this kind of system. By contrast then, and again, this was not is not a priori, although by now we replicated what I'll show you in a minute a few times. A counter proposal is that stability and flexibility actually map onto orthogonal dimensions and are independent processes. So in this case, you could argue that, well, maybe the level of task set shielding provided by frontal-parietal cortex is not directly yoked to the how easy or hard it is to open the gate to working memory, but rather that these two things are independently regulated in this little toy model. The key here is that this sort of model allows people at times to be both stable and flexible concurrently, which I know sounds surprising, but we have found a lot of evidence for that being the case. So we went in, and this was a previous grad student of mine, Raphael Geddes, who's now sadly in the pharmaceutical business. Good for him, kind of sad for me. I'm sure he's making good money. And what we set out to do was, in fact, when we first started, it was like, oh, everybody assumes that you have this trade-off between stability and flexibility, and there's some suggestive evidence of that in the literature, but nobody ever like tests this in a really like coherent manner and really says, hey, let's vary demands on stability and flexibility independently and concurrently. And we thought, oh, yeah, we can design a task like that and show, once and for all that you get this nice seesaw relationship. So this is what we set out with. And this is the task we use. I've already introduced you to the basic task. So this is, again, the task switching protocol where we vary between tasks of parity and magnitude estimation of these numbers. Now, what I didn't tell you is that this task also can incorporate a really nice test of stability or conflict component, because if you usually you perform this task with just two response buttons, and so you map both, say, even and smaller than 5 on one finger and larger than 5 and odd on the other finger. That means that half of those numbers will be incongruent across the tasks. They would require different responses depending on the task set, whereas half of them are congruent. You push the same button no matter which task it is. Does that make sense? Very good. So you can, of course, you get, in fact, a very robust congruency effect in this kind of setup. So a cross-task interference effect. So people are on average much slower to respond to those incongruent stimuli than to congruent ones in the setting also. This gives you the nice situation where in the same task, we can look at switch costs and cross-task interference effects. So measure of flexibility, measure of stability. That's not enough for us. We also want to vary the demand over time, of course, because we're interested in how these processes are regulated. So what we do is that we manipulate across blocks independently the proportion of incongruent trials, so how many of these cross-task conflict trials you get, as well as the proportion of switches. Now, the flexibility stability trade-off assumption would argue that when you increase the number of incongruent trials, you get more stable, right? You have to get more focus. That's the conflict adaptation effect. Being more stable should make you less flexible. So in blocks with a high rate of incongruent trials, you should have a high switch cost, because if you're very stable, then you should have trouble switching. Conversely, in blocks where you have a high switch rate, you should in fact be very flexible, good at switching, but suddenly get a very high interference effect because you are not protecting your task set properly, okay? This is the assumption that we had going in. We thought, oh, let's show this really nicely. Instead, what we found is that the two play out completely independent of each other. So it turns out that if you vary the proportion of switch trials, of course, the switch cost goes down as switch trials go up. So this is just replicating this blockwise switch proportion effect, but that has no effect on the congruency effect. Conversely, altering the proportion of incongruent trials reduces, or increasing the proportion reduces the interference effect, but does nothing to the switch cost. So there's evidence for independent regulation of flexibility and stability in this paradigm. And we, in that particular paper, we had like 3 versions of this and we replicated it. And right now, about to come out, we have like another replication of this with some additional tweaks. So it's seems to be a pretty reliable finding, and it's very surprising from the point of view of the classic stability trade-off, flexibility trade-off assumption. So this is why we had to, come up with a new explanation for it and came up with a 2-dimensional model that arguably also in some ways fits better onto the neuroscience literature, where actually you can, people have found manipulations that selectively affect the basal ganglia or the prefrontal cortex, and they can show a fair bit of independence of each other. This is, of course, sort of descriptive and interpretive. We also have modeled this in the meantime, where basically we just want to have a formal demonstration of showing that, hey, a 1-dimensional model will do a lot worse at accounting for these empirical data than a 2-dimensional model would. The details are not actually that important right now. In fact, we model it in a variety of different ways. The winner always comes out the same, luckily. But the basic idea is that, hey, we have both models learn about the proportion of switch trials, and they learn about the proportion of incongruent trials, and they feed this into adjustments of flexibility. The 1-dimensional model can only shift the fader around along 1 dimension. So the more flexible you get, the less stable you get. So you have to make trade-offs. Whereas a 2-dimensional model can do, of course, that's across 2 independent dimensions. And jumping quickly to the actual data. Sorry, this is a little bit busy, so I'll focus you in on the important part. So actually, let's go one back. The 2-dimensional model, this is the empirical data, the black data points here. And the brown ones are the simulator or fit data from the model, the posteriors in this case. You see that the 2-dimensional model can account for all of the conditions very well. So it's just very close to gets very close to the empirical data. However, the 1-dimensional model has some major problems, but it has the problems in a very selective condition, and it makes a lot of sense. So if you look at the condition where both the switch rate is high and the incongruency rate is high, this is the condition where you have to try to be both stable and flexible at the same time. This is impossible with a unidimensional model, right? Because you can only, if you pull the fader this way, by definition, it gets away from the other side. So you end up somewhere in the middle if the model gets pulled in both directions. Therefore, the model is not able to account for the fact that these empirical data points in this condition show both less switch cost than the condition where these demands are low, and smaller congruency effect than in the conditions where these things are low. You can't get this with a 1-dimensional model. You can get it easily with a 2-dimensional model because they're, both of these things can go up and down independently of each other. All right, this brings us to the end of the talk. Well, even though I call it an interim conclusion, trust me, you can get out of here really soon. when demands on task process and switching are manipulated independently and concurrently, it turns out people can actually adapt them separately without affecting each other. We think this is quite exciting, and it's a real sort of twist in how we think about how this works. Others are not so excited. Actually, just yesterday in the new issue of the Nature Review Psychology, there were the two angry comments on my thing and two responses, which is of course nice, as you always get the last word as the original author, which is annoying if you're not that, but if you are, it's very nice. So there you go. Feel free to read up on it. So this is our proposal. The bigger take home, again, as I told you, I'm reselling you the premise as the conclusion. Task focus and switch readiness can be adapted according to the same learning principles, but regulated independently of each other. And this comes down, in this particular case, to these incremental learner of task focus that might determine how much, say, the frontal parietal cortex protects the current task set, and independently of that incremental learner of the ease of allowing another task set into working memory. There's a whole second part to all this, where there's a more reactive learning mechanism that also affects both of these processes, a form of episodic reinstatement of control level. So you might re-encounter, for example, situations you've seen in the past. You don't have to sort of learn from scratch what the current demands are. You can just say, oh, this was difficult. I'm going to reinstate that from memory. This is something I didn't talk about, but it's also part of that paper if you're interested in reading more into this. With that, I'll thank you guys very much for your attention late in the afternoon. Don't get ahead of yourselves. We're going to be here for a few more minutes. No, thanks to you lab members and funders and so forth. And we had a lot of fun. This meeting was a really, really, really exciting meeting. I'm glad to be back after 20 years or so. Hopefully we'll do it again. And I will no longer stand between you and the pub or wherever you're going next. All right, thank you.
Thank you, Tobias. That was amazing. So I think we've got time for a couple